the fate of the universe, hidden in a cup of coffee. You make a hot cup of coffee in the morning. At first, it is almost too hot to drink. So you leave it on the desk, check your phone, read something, or get distracted by work. A little later, you come back and the coffee is lukewarm. Now imagine a glass filled with ice on a summer day. At first, the ice cubes are hard and clear, clinking against the glass. But slowly they shrink, and eventually they disappear into the water. These things are so ordinary that we hardly ever question them. But let us make the question strange again. Why does hot coffee always cool down? Why does ice melt? Why does melted water not suddenly reorganize itself into ice again while sitting in a warm room? And why does the surrounding air never spontaneously gather its energy together and reheat your cold coffee? Surprisingly, hidden inside these simple questions are some of the deepest ideas in physics. Thermodynamics, entropy, irreversibility, the arrow of time, the nature of life, and perhaps even the ultimate fate of the universe. In other words, the reason a cup of coffee cools may contain a clue to why time appears to move in only one direction, and maybe even to where the universe itself is heading. So first, what does it actually mean for something to be hot? We often imagine that a hot object simply contains more heat. That is not completely wrong, but physics asks us to be more precise. If we look deep inside matter, atoms and molecules are never truly still. They move, they vibrate, they collide. In hotter matter, the microscopic motion is, on average, associated with a higher energy distribution. In colder matter, that thermal motion is lower. Temperature is therefore a macroscopic way of describing the statistical state of an enormous number of microscopic particles. And here we need an important distinction. Temperature and heat are not the same thing. Temperature describes a thermal state. Heat is energy transferred because of a temperature difference. So heat is not simply a substance stored inside an object. It is energy in transit. Now imagine a cup of coffee at around 70 degrees Celsius in a room at 20 degrees. There is a large temperature difference between the coffee and its surroundings. Because of that difference, energy begins to flow. Some passes from the coffee into the cup through conduction. Some is carried away by moving air through convection. Some leaves through thermal radiation. And some is lost through evaporation from the coffee's surface. All of these processes occur at the same time. So when we casually say, the coffee is cooling, what is really happening is a complicated exchange of energy between the coffee and the rest of the world. But here is the key point. The energy does not simply vanish. Energy that was relatively concentrated in the coffee becomes distributed into the cup, the surrounding air, the table, the walls, and eventually into a much larger environment. As time passes, the temperature difference becomes smaller. Eventually, the coffee approaches the temperature of the room. This is thermal equilibrium. You could say that nature tends to erase thermal differences. Not because coffee has some desire to become cold. There is no intention involved. The reason is statistical. There are overwhelmingly more microscopic arrangements in which energy is spread among many degrees of freedom than arrangements in which it remains highly concentrated in one small place. Now let us turn to ice. An ice cube in a warm room is colder than its surroundings. So this time, energy flows in the opposite direction. Heat moves from the warmer environment into the ice. The water molecules gain energy. The ordered solid structure can no longer be maintained, and the ice melts into liquid water. At first glance, cooling coffee and melting ice seem like opposite processes. One thing becomes colder, the other becomes warmer, but physically they tell the same story. Both processes reduce a temperature difference. Hot things cool, cold things warm, and eventually systems tend toward thermal equilibrium with their surroundings. But now something very interesting enters the story. Us. A cup of coffee can reach room temperature and nothing is wrong. A stone can reach room temperature. A chair can reach room temperature. But what happens if the human body simply reaches complete thermal equilibrium with its environment? For a living organism, that is a very different matter. The human body must maintain its core temperature within a narrow range around 37 degrees Celsius. When the environment becomes hot, blood flow to the skin increases. We begin to sweat. And sweat is not important simply because water appears on the skin. The critical process is evaporation. For liquid water to evaporate, it must absorb energy. That energy comes partly from your body. So evaporation removes heat. That is why sweating can cool us. In cold conditions, the body does the opposite. Blood vessels near the skin constrict to reduce heat loss. Muscles may begin to shiver. Shivering generates additional heat through muscular activity. So when your body trembles in the cold, it is not merely expressing discomfort. It is actively spending energy to defend its internal temperature. And that reveals something profound. Life does not passively fall into equilibrium. It continuously works against it. Of course, living organisms do not violate thermodynamics. We cannot escape the laws of energy and entropy. Instead, life remains out of equilibrium by continuously taking in energy and matter, using them, and releasing heat and waste back into the environment. This is why we can describe life as a non-equilibrium system, and perhaps there is a more poetic way to say it. Life is the process of continuously postponing equilibrium. That also helps us understand why we feel heat and cold. We do not experience temperature simply as a number on a thermometer. 30 degrees Celsius does not always feel the same. If strong wind is blowing, it may feel cooler. If humidity is high, it may feel much hotter. Why? Because what matters to the body is not only the temperature of the air. What matters is how efficiently heat is moving between the body and the environment. Wind continually replaces the warm layer of air near the skin and can increase convective heat loss. High humidity creates a different problem. When the air is already filled with water vapor, sweat does not evaporate as efficiently. You may be sweating heavily and still not cool down well. That is because the real cooling power of sweating lies in evaporation, not merely in producing sweat. And this brings us directly to heat illness. The human body is always generating heat. Your brain is active. Your heart is beating. Your organs are carrying out metabolism. Your muscles produce even more heat when you exercise. Normally, the body sends that heat outward. But in very hot and humid conditions, heat loss can become insufficient. The body continues producing heat, but the pathways for releasing it become less effective. The cardiovascular system works harder to send blood toward the skin. Sweating causes loss of water and electrolytes. If the body's regulatory capacity is pushed beyond its limits, heat exhaustion can occur. And in more severe situations, heat stroke can develop as normal thermoregulation fails. From a physics perspective, heat illness can be described very simply. The body generates heat, but cannot transfer enough of it to the environment. The problem is not merely that the air is hot. The problem is that the flow of energy out of the body becomes restricted. Now let us go deeper. Why does nature tend to reduce temperature differences? Why do things spread out? This is where entropy enters the story. Entropy is one of the most misunderstood ideas in physics. It is often described as disorder. That can sometimes be useful, but it is incomplete. A better intuition is this. Entropy is related to how many microscopic arrangements are compatible with the same macroscopic state. Imagine every molecule of air in a room somehow gathered into one small corner. Physics does not absolutely forbid such a state, but there are extraordinarily few microscopic arrangements that produce it. Now imagine the air spread throughout the entire room. There are vastly more ways for the molecules to be distributed like that. That is why air naturally spreads. Spray perfume in a room and its molecules disperse. Drop ink into water and the ink spreads. But you never see dispersed perfume molecules suddenly rush back into the bottle. You never see mixed ink spontaneously reorganize itself into one perfect drop. And cold coffee does not spontaneously become hot. All these processes have something in common. They move from relatively special, constrained states toward overwhelmingly more probable states. That is what entropy increase captures. And now we reach one of the deepest questions in physics. Many fundamental microscopic laws appear almost indifferent to the direction of time. If you filmed two ideal particles colliding and played the film backward, the reversed motion could still look perfectly consistent with the laws of mechanics. At the microscopic level, many equations allow both time directions. But our everyday world is not like that. A broken cup does not reconstruct itself. Ash does not become paper again. An old person does not naturally return to childhood. And cold coffee does not suddenly reheat itself. So where does the direction of time come from? One important answer lies in thermodynamics. The future is associated with the direction in which entropy increases. We do not know that time has passed only because we look at clocks. We know because the world carries irreversible traces. Ice has melted. Coffee has cooled. A candle has burned down. A face has aged. These processes allow us to distinguish before from after. This is called the thermodynamic arrow of time. It does not necessarily mean that entropy somehow creates time itself. That would be too strong a claim. But the direction of macroscopic irreversibility is deeply connected to the direction we experience as the future. And now an even stranger question appears. Why do we remember the past but not the future? Memory may feel abstract, but memory is physical. For the brain to form a memory, physical states inside neural circuits must change. Synaptic strengths change. Proteins may be synthesized. Networks are reorganized. Something is physically recorded. The same is true of a computer storing a file. Something in the physical device must change. Photography works the same way. Light changes a sensor. A fossil records an earlier organism. Tree rings preserve the history of seasons. A scar preserves evidence of an event. The past leaves traces, and those traces are created through physical processes that consume energy and generate entropy. Perhaps this is one reason the psychological direction of time is so closely aligned with the thermodynamic one. We remember the direction in which records accumulate. Maybe time is not experienced simply because clock hands move. Maybe we experience time because traces accumulate in one direction. Now consider life again. Living organisms appear highly ordered. DNA contains precise structure. Proteins fold into specific shapes. Cell membranes separate inside from outside. Organs maintain coordinated functions. The brain sustains highly organized electrical and chemical activity. If entropy tends to increase, how can this degree of organization exist? The answer is that life is not a closed system. We eat. We breathe. We absorb energy. We release heat. We release carbon dioxide and metabolic waste. Living systems can maintain local order while increasing the entropy of their surroundings even more. Life does not defeat entropy. Life exports entropy. It maintains its internal organization by continuously dissipating energy into the world around it. And that means being alive is expensive. The heart cannot simply stop. Cells must continuously repair damage. Proteins must be replaced. Ion concentrations must be regulated. The brain must constantly process and maintain information. Order requires energy. Perhaps life is not the absence of decay. Perhaps life is the process of repairing itself slightly faster than it falls apart. Now let us move away from the desk and look at the universe. Stars shine because the universe contains differences. Differences in temperature. Differences in density. Differences in gravitational potential. The sun is hot. Space is cold. That temperature difference allows energy to flow. Life on Earth exists partly because our planet receives relatively concentrated energy from the sun and radiates lower quality energy back into the colder universe. Life exists inside a flow. But what happens in the extremely distant future? Stars eventually exhaust their fuel. The rate of star formation declines. Sources of usable free energy become rarer. If the current accelerated expansion of the universe continues broadly, as described by the standard cosmological picture, the universe may become increasingly cold, dilute, and unable to sustain large energy differences. One famous long-term scenario is called the heat death of the universe. The phrase sounds as though energy disappears, but that is not the idea. Energy may still exist. What disappears is useful difference. If energy becomes too evenly distributed, there is less ability to perform work. A river flows because there is a difference in height. Electric current flows because there is a difference in electrical potential. Heat flows because there is a difference in temperature. Life also depends on differences. Without gradients, there is no flow. Without flow, there is no sustained structure like life as we know it. In this sense, a cup of coffee cooling on your desk and the extremely distant future of the universe belong to the same thermodynamic story. Both involve the loss of usable differences, so the statement that the fate of the universe is hidden in a cup of coffee is not as exaggerated as it first sounds. Now let us ask how this might look from an IG, or information gauge perspective. First, an important clarification. We do not need IG theory to explain why coffee cools or why ice melts. Standard thermodynamics and statistical mechanics already explain these phenomena extremely well. An IG interpretation should therefore not be presented as a replacement. It is better understood as an additional informational way of asking what these processes might mean. Consider the hot coffee again. At the beginning, energy is relatively concentrated in a small region. As time passes, that energy spreads into the cup, the surrounding air, the table, the walls, and countless microscopic degrees of freedom. The microscopic information may not simply disappear. In principle, if you somehow knew the exact state and correlation of every relevant particle, you might reconstruct enormous amounts of information about what occurred. But in practice, that information becomes distributed across an unimaginably complex network of correlations. To restore the original hot coffee spontaneously, you would need to coordinate an astronomical number of microscopic variables with extraordinary precision. So from an IG perspective, we might interpret entropy increase not simply as information being destroyed, but as information becoming distributed across a much wider relational network. The information becomes harder to access locally. It becomes encoded in correlations. It becomes spread across the environment. In this language, the arrow of time might be interpreted as the direction in which information becomes increasingly delocalized and embedded in broader relational structures, not necessarily lost, but increasingly difficult to reverse. Memory becomes interesting from this perspective as well. An event leaves a trace. Light changes a camera sensor. Sound changes a recording device. Experience changes the physical state of the brain. The past becomes connected to the present through physical records. Using IG language, one might say that time's direction is associated with the asymmetric accumulation of relational information. But this must remain a hypothesis or interpretive framework. It is not established thermodynamics. It is a way of asking whether the physical arrow of time and the spreading of information might be described within a common relational language. And when we look at life through this perspective, another possibility appears. A living organism maintains boundaries. It separates inside from outside. It regulates temperature. It maintains ion gradients. It repairs molecular structures. It stores memories. It continuously controls flows of energy, matter, and information. So life can be viewed as a non-equilibrium structure that actively maintains certain informational and physical distinctions. And heat illness is fascinating in this context. When the environment becomes too hot and too humid, the body's ability to maintain those distinctions begins to weaken. Thermally, it is a heat balance problem. Biologically, it is a failure of homeostasis. From an informational point of view, it can also be seen as the destabilization of a complex regulatory network that normally keeps the organism within a narrow, viable range. Again, this interpretation does not replace physiology or thermodynamics, but it gives us another language for thinking about what life is doing. Life does not violate the laws of nature. Life uses them. It creates temporary organization by consuming energy and releasing entropy into the environment. We cannot defeat entropy, but for a while, we can maintain order. We cannot stop time, but we can create memories. We cannot prevent all gradients from eventually fading. But while we are alive, we constantly create and preserve differences. The difference between body temperature and room temperature. The difference in ion concentration across a cell membrane. The difference in electrical potential across a neuron. The difference between hunger and satisfaction. Between not knowing and understanding. Between who we were yesterday and who we are today. Maybe life is, in part, the ability to sustain meaningful differences. Leave coffee alone and it cools. Leave ice in a warm room and it melts. But even when a human being appears completely still, the body is never truly still. The heart is beating. The lungs are exchanging gases. Cells are transporting molecules. The brain is updating its network. A living body is never in complete equilibrium. And perhaps that gives us another way to think about being alive. Maybe being alive means continuously postponing equilibrium. Not forever. We cannot postpone it forever. But during that interval, we love. We think. We ask questions. We build things. We preserve memories. We give meaning to differences. The universe seems to move towards states in which differences gradually fade. Yet life temporarily uses those differences to create structure and meaning. Now return to the cup of coffee on the desk. A few minutes ago it was hot. Now it is lukewarm. At first that may seem only disappointing, but perhaps you can now see something else inside it. Molecules are moving. Energy has spread. Entropy has increased. The thermodynamic arrow of time points in one direction. And in the middle of that same flow, your body is spending energy to maintain its temperature, its structure, and its memory. We cannot see time directly, but we can watch coffee cool. We cannot see entropy directly, but we can watch ice melt. We may not completely understand the essence of life, but we can see what life requires. A continuous intake of energy, a continuous release of heat, continuous repair, continuous regulation, continuous creation of memory, a constant effort to delay equilibrium. Perhaps being alive means this. In a universe where everything tends toward equilibrium, we temporarily protect our temperature, our structure, our boundaries, and our memories. Coffee cools, ice melts, and time moves forward. But inside that flow, for a brief moment, life creates warmth, preserves differences, and leaves a trace. And perhaps that is one of the most beautiful things thermodynamics can teach us about being alive. Thank you for watching. This has been ThothSaem's Science Catch.